So in the last chapter, we learned that for flow over a heated surface, let's say, the temperature is a function of x, y, Reynolds number, and Prandtl number. Okay, so that's a general statement. But in this section, what we'll learn is for this kind of a flow of a fluid over a surface, quite often there is only a thin layer of fluid called boundary layer right near the surface. That's all we need to care about. That's where all the action is. So that's what this section is about. So I will try to show in three different ways that it is this thin layer near the surface. So this is the surface, the thin layer near the surface matters, and that's all we need to care about. So here, this one is a complete solution of those equations. So the Navier-Stokes equations plus the heat equation for flow over a heated surface. So it's a heated plate and a colder fluid is flowing over it. So you can see right there from the solution that the effect of the heated plate doesn't go very far. It is restricted to a thin region near the surface. And I did not assume it to be thin. The solution came out this way. So if we do the full solution, we find that these areas here, they are not contributing to anything. So all the actions are happening here. And this is for heat transfer, so it goes from red to blue. But also for velocity, you can see by the time it reaches here, after that the velocity stays the same. So velocity change is also restricted to a thin layer. So we see that the thin layer over the surface is where the action is. So in the last slide, we saw the solutions of the equations. So here we will try to see from experiment. Okay, so what we have is a plate over which a fluid is flowing. Okay, and what you see experimentally is, although the velocity of this fluid is 0 right on the wall, we don't see the effect of the wall. So all of these regions, the fluid flows just fine. So the effect of the wall is not felt far away from the plate. Since the velocity of the fluid is 0 on the surface, the velocity must go from 0 to this velocity over some distance. In fact, you can see that if you have an expanded view near the surface. So this is an expanded view showing velocity is 0 on the surface, but it quickly reaches the free stream velocity. So this is an expanded view of a region near the surface. So again, this is making the point that only a thin region near the solid surface matters. So after the solution to the equations, then we talked about the experimental results, And now we're talking intuition. So what you just saw was Niagara Falls, a lot of water flowing over a surface. So for fun, imagine it if it were possible to go underneath the falls, which we can, but imagine it was possible to position yourself this way with your back this way, so there is the flow right over your back. Okay, so the fluid flow is over your back. Imagine if this were possible. Now, if we can still stay put and stay alive, water will flow over your back. Water will flow just fine, but the velocity of water on your back is zero. It would still be zero. So does that mean we kind of slowed down the Niagara Falls a little? Possibly not. Would you expect the flow on the top, all these regions, would you expect it to be any different? Possibly not. But on the back, it is still zero. So what does that mean? It means the fluid velocity goes from zero to the maximum very quickly, meaning over a very thin region. So the effect of the stationary surface on the fluid is restricted to a thin layer. This is the velocity boundary layer. Likewise, if we think of this, our body typically would be warmer than the water of the Niagara Falls. So we do not really expect to have warmed up the Niagara Falls water. But the fluid layer right on our back would be at the temperature of our back because it is stuck to the back. Okay, so the temperature goes from our back temperature to the water temperature over a very thin region. This region over which the temperature changes from the surface to the fluid is the boundary layer. But the main point here is intuitively, if we just think through, then also we can see that the action is likely to be restricted over a thin layer. So only a thin layer over surface is relevant. So from theory, that's solving the equations, from experiment and intuition, we kind of see that only a thin layer near the surface is really relevant. This thin layer is termed the boundary layer. Now, just to bring in some everyday example, I don't know if you noticed that when we turn on the shower, where the water hits first, we feel the coldest or the warmest depending on the water temperature in relation to the body. I don't know if you notice that, but I do. And so bringing this example, if we think of our back as a, a surface over which the flow happens, then here, for example, is our ideal surface, and let's say it's a heated surface. So heated surface over which colder fluid is flowing. Okay, so then as the fluid is flowing over the heated surface, so here as the fluid is flowing over your back, it first hits here, but as it's flowing down, because it's flowing over a warmer surface, then it keeps getting warmed up. So then the layer of fluid that the back will be warming up would keep increasing with a distance. And that is kind of exaggerated here, that on the surface is the warmest, the red, and then over here it's blue. The actual thickness is, it's very thin. This one, this figure is more realistic. This other one is expanded for better view. So it goes from the hot surface of the bag to the colder fluid over a thin region, and that region is called the thermal boundary layer. And you can see the boundary layer increases as we go this way, for the simple reason that as the fluid is flowing this way, it's picking up heat. So more of the fluid gets warmed up, so the warmed up layer of fluid increases. And this layer is different, this thermal boundary layer is different from velocity boundary layer. So the velocity boundary layer has to do with how far the effect of the wall makes the velocity to be 0, so it slows down. How far does it go inside the fluid? So you can see by the time it gets to here, the velocities are already at the maximum. So the velocity boundary layer would be given by this part. If you go further here, then the velocity changes this way, and so this is where it stops changing. So then this is my velocity boundary layer. Okay, so the velocity boundary layer is different from thermal boundary layer. Velocity boundary layer has to do with the viscous effect, how far it goes, and the thermal boundary layer has to do with heat conduction, how far does it go. So the same thing here on the back, the exaggerated one, this is my thermal boundary layer, but the velocity boundary layer is some different value. Okay, so this one is thermal, and then this one is velocity. So there are two different boundary layers that form. Now we can actually calculate these boundary layer thicknesses in at least in some cases. And for this common one, flow over a heated flat plate. Okay, so this is my heated flat plate, and this is colder fluid flowing over it. So for this, we can actually do the full calculation analytically, and we can find a formula for this velocity boundary layer. So what is that? So as you can see, if I plot how the velocity goes from 0 on the solid surface to the maximum value, so of course the velocity keeps changing. It doesn't suddenly go to the maximum value. So we define the thickness of the layer to be where 99% of the change. So it has reached 99% of the maximum velocity. That thickness is what we call the velocity boundary layer thickness at that location. So that's the location measured from the upstream. And so this velocity boundary layer always exists, because as soon as fluid flows over a surface, then the velocity has to be 0 on the surface. So there has to be a distance over which it goes from 0 to the maximum. So this always exists. Velocity changes are confined to this layer, and this is my formula. So the thickness, this is my delta velocity. The velocity boundary layer thickness here is given by this is the delta velocity, and delta velocity is given by this quantity where Reynolds number is u infinity rho x over mu, where x is the distance to that point, because the thickness keeps changing. If you look at here, it is the velocity goes to the maximum over a thinner region. It's basically the viscous effects have not reached that far because the flow has just started. So then I can calculate this velocity boundary layer thickness. Of course, in practice, for the kinds of things we deal with, it will be of the order of few millimeters in many everyday applications, but it can also be kilometers. It depends on the particular situation. So thermal boundary layer, in contrast, it doesn't always exist. If the fluid were at the same temperature at the heated surface, then there is no discussion of a thermal boundary layer. It's all at the same temperature. So there is no thermal boundary layer. So when there is temperature difference, then the temperature difference happens over this distance. So here it shows by color, the fluid flowing over it is blue and the surface is red. So at the same location as the velocity boundary layer, the thermal boundary layer would be given by this part, which is in this case thinner. It doesn't always have to be thinner. It depends on the fluid properties. So the thermal boundary layer is again defined where 99% of the thermal changes take place, and that is related to the velocity boundary layer because it's happening because of the velocity boundary layer, but there is also other parameters. So in relation to the viscous effects, how fast does the thermal effects propagate from the wall, that's given by this Prandtl number. So we can calculate the thermal boundary layer this way.